So I would like to introduce Caroline Wormell from University of Sydney, speaking about two classes of highly effective discretisations. Thank you.
Thank you. Thanks, Isaiah. Yeah, it's thanks to the organizers for inviting me, and so far it's been really, really nice hanging out with you all and talking about numerics in chaos, or sort of computation in chaos. So what I want to talk to you about today is something that is coming from more of an applied direction. So perhaps engineers maybe 15 years ago discovered Koopman operators and started computing with them and studying them independently. And I mean, this is a bit of an attempt to try and inject some ideas from transfer operators into what they do. So I should just write down what a Koopman operator is perhaps if you have a dynamical system, let's say a nonlinear dynamical system in general, and you want to turn it into a linear dynamical system, perhaps the simplest way you can do that is look at function composition. So I take a function, so maybe I have some function f, some manifold, and I look at functions phi on my phase space, and I just say I compose with it. And perhaps this could be stochastic. Could I be? And if it's stochastic, then I need to put an expectation here. So it's kind of, somehow what this is telling us is that the Koopman operator gives this kind of expected value of phi one step into the future. And of course, this is, as we know, this is adjoint to the transfer operator. So in general, let's say psi times k phi with respect to Lebesgue is the transfer operator of psi times phi with respect to Lebesgue, transfer operator, which needs no introduction. And so somehow, everything that we know about the transfer operator kind of applies to the Koopman operator. We can study this to think about correlations. We can think about large deviations. We could probably even think about linear response. Maybe we could, I don't know, understand number theoretic properties of whatever, of our dynamical system by studying the Koopman operator as well. So I suppose we can ask ourselves, how do we actually compute this with this guy? Because it is an infinite dimensional operator acting on, an infinite dimension, an infinite dimensional space of functions that I've not even told you what the space is or what the norm is, but let's be pretty theoretical here. We want to kind of compute this. An approximation of this operator and then maybe study its spectrum, for example. And the way that there are many ways to do it. I mean, we've been seeing ways to do it all week with, say, Isaiah's talk and Julia's talk and Warwick's talk, and perhaps some other talks as well. But I suppose I can look here and see who else did that. But I'm going to perhaps the sort of simplest way to think maybe you could do it is just imagine that you have very little information about your operator. Let's in fact imagine that you have just a collection of data points, which lie in your manifold. And I mean, maybe we could even say a little bit more. Perhaps we could hope that these xi's are kind of randomly distributed and sort of distributed according to some measure. And maybe you have a sort of set of observations of these guys. So, either you can choose some functions, psi naught, let's say up to psi b, and you have, say for x1, we can observe psi naught of x1, psi 1 of x1, and so on. And perhaps we can do the same for all our other data points. So I'm just, making the notation here. And we can construct a little matrix of these guys. We can also, I mean, I guess we need to know something about that dynamics as well. So we could hope that we perhaps also know what f of x1 is, f of x2, f of x3. And so if we know f, then, if we know f and we can just choose some data points in our manifold, this is very easy. But this also actually works if we can't, like if we don't know f or we don't really know what x1 is, well, let's say we don't know f, we can, if we have some time series, say, of our dynamical system that we've observed, here's some weather, and we looked at our weather system and we got one of these, we get, again, a matrix of f of these guys. And so morally, this kind of looks like psi naught with the Koopman operator applied in a very, very, very moral sense. And this suggests that what we want to do is that we can approximate our Koopman operator by least, well, let's hope that we can approximate it by least squares. So the way, of course, that you do that, if you remember from first year statistics, maybe second year statistics, I didn't learn very much in first year statistics, is that you basically look at the covariance between your previous time and your future time, and then you remove it by you sort of remove the correlation, the autocorrelation between psi naught. And so this ultimately approximates your infinite dimensional Koopman operator by some it approximates your Koopman operator by some matrix. And so you can think of this as kind of the approximation of the Koopman operator in the basis given by psi naught up to psi b in your observation dictionary. And so then you can ask yourself, okay, well, I have some matrix here. I know what the spectrum of this matrix is. I'm going to call it. I decided to call it K as well. Well, let's call this the Koopman operator curly K. This is a matrix with respect to, I guess, my points, number of points, and also my number of bases, my observation dictionary. So I'll just notate it like by that. So we can ask ourselves, again, does sigma K and B, as let's say we increase our number of observations, so we get more information about our system, and perhaps we also increase the kinds of observations we look at, does this converge to the spectrum of the Koopman operator? And then, of course, the question is, well, what space? And if you are a chaos person, you would know that there are lots of different spaces here, and it probably doesn't matter too much because the point eigenvalues that you get here will always be the same. And then you get some essential spectrum in the middle, depending on basically how well you chose your space. Engineers don't know this. And so they always think about this as L2. And the thing about the L2 spectrum of the Koopman operator for a stochastic system is that it is the kind of real space. It's the same spectrum. The spectrum in L2, the Koopman operator, is the same as the spectrum in, well, say it's has some analytic kernel. It's like from an SDE has smooth coefficients or something. It's the same, whatever space you choose, it's the same spectrum. So for stochastic cases, it looks like this is true. But for deterministic systems, what they like to do is study it in L2, and we know that for this one, the spectrum of L2, let's say for a measure preserving, like L2 mu usually, for measure preserving invertible map is the unit circle. And this is really boring because it's the same for every map. So we could ask ourselves, well, what if it's the spectrum? What if we replace this by saying the real world polycult resonances? And so the question that I'm going to try and say today is, does this happen? And the answer will be yes, but then we could ask ourselves, what happens? We have two limits here, right? So we can take our data to infinity. We can also but then we have to take our basis functions to, we have to do this in some order. And the problem with taking limits in some order is that in practice, we only have one, we only have one timeline of t go to infinity, and we can't study two timelines. We need to take some limit here. And so usually your data is fixed, and so you can maybe adjust the number of basis functions you have. You need to figure out what this guy should be. So that then, you can compute along here and you get something like this. You get some convergence. And okay, so I should tell you what the answer is for okay, so I should tell you some kind of what happens now. I'm going to tell you what happens in this limit. And the answer is going to be very simple, perhaps too simple. I'll tell you what happens in this limit, and then I'll try and tell you something about the interaction. And I think the exciting thing about the interaction is that it really goes into the functional analytic theory of transfer operators. And so everyone here who spent a lot of time trying to get good bounds on the essential spectrum, the essential spectral radius of a transfer operator, this is intimately connected with this kind of limit. Okay, so what does our data look like? What's our data system look like? So I guess if we try and think about what this kind of matrix thing composed of a bunch of other matrices, so this looks like, we'll call this here psi naught naught, and we'll call this here psi naught 1 for obvious reasons, being that it's the convergence of these guys. So if we look at psi naught naught, we look at, say, the ijth component, it's like a covariance between these different observables. So I'll write it out. It's a sum over our number of data points of psi I of x and psi j of xn. And I guess we also need to take a thing there. Same thing with psi naught 1. And of course, well, if we normalize these, we can see that they look a lot like expectations with respect to our points. And so if we imagine here that our psi xi's are, well, let's say they're evenly sampled in an appropriate way, maybe this kind of convergence, let's say that this is a we're looking at an interval. This is a these are evenly spaced. Then let's say periodic interval, then we know that these might converge really, really fast. So this is something that Julia and Oscar and Wolfram Just have done, I think. But a sort of more natural thing to do, imagine if you're an engineer and you're studying a fluid flow, it's in this infinite dimensional space. And so what you're actually doing often is you're not trying to sample your whole space with these x1s in some kind of intentional way. What you're doing actually is you're taking a time series and you're saying xn plus 1 is f of xn. And you're hoping that, somehow this samples, but by doing this kind of iteration, you're sampling the ergodic measure. So actually, this guy here is x2. So this is what makes this f psi 1 really easy to fill if you do this, because you just fill it with, it's just this shifted over by a column, by a row rather. Anyway, but the point is then, if we imagine we have a chaotic system or indeed a stochastic system, we get a central limit theorem. And so this is going to look like some long-term limit with respect to our ergodic measure plus some random term, some random error, central limit theorem error. And similarly here. And the kind of upshot of this is that if we try and understand what our Koopman operator looks like, it looks like the, let's call this some kind of limiting matrix I define this to be our limiting matrix. This looks like psi naught naught. Well, okay, what it is it's psi naught naught inverse psi naught 1. But this, provided that psi naught naught is reasonably well conditioned, we can write it as the infinite limit plus some random matrix. With hopefully reasonably uncorrelated coefficients. And so then this suggests that, in a kind of silly sort of way, that the spectrum of this Koopman operator that we can compute from our time series looks like some sort of spectrum of, let's call it KB. So some continuum limit Koopman operator plus order 1 on n, 1 on root n. Good. So that seems so far so easy. And this works for any kind of, I suppose, dynamical system where you have a central limit theorem. But it starts to give you, yeah? This one? Oh, yeah, totally. Sorry, I'm sorry for my handwriting. It probably should be a bit more even. All right. So this is good for this at top limit there, but then we've got to think about the next limit. So I suppose that's the thing about this one is now that we're it's a bit harder to understand because now we're trying to approximate, like all that was finite dimensional. We're just saying a matrix looks like another matrix. But now we've got to say a matrix looks like a kind of infinite dimensional operator. And that's yeah. Yep. Sorry, it's not obvious what? It's not obvious that the error is small in some null limit. Yes, yes, absolutely. So yeah, so the catch is the constants here could be huge. Yeah. Yes, it should depend. It should depend. It should depend on the number of basis functions here. The constant. It's kind of like for large enough n, it's independent of n. As you take n to infinity. Yes. Yeah. 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 So now let's imagine that we've totally wiped out this error because we've taken n to infinity, and now we want to understand how this spectrum looks like, the spectrum of the actual Koopman operator. And so there's no one answer to this. As we know, dynamics is a awful trade where you can't say anything about very much. But we do know that we can say things about uniformly expanding maps of the torus in one dimension where these things are analytic. This is a thing that we know so much about. And so in this context, we know that, a second, what have I done here? Yes, okay. In this context, we know that, well, okay. I've just got to find my notes. Okay, here we are, yes. Well, in this context, actually, we know that we can approximate well, let's say our Koopman operator, okay, our transfer operator, let's say this, our transfer operator is in various spaces, is quasi-compact. In, I don't know, let's say W, so Sobolev space, let's say R2 for R in R bigger than 0. Strictly bigger than 0. So for, but I should just write this down in case F analytic, uniformly expanding on R on 2 pi Z to itself. So, you know, some sort of circle map. And so okay, we should say, well, what does this mean quasi-compact in R2, blah, blah, blah. So this guy here is the space of functions. I'm going to write it in terms of Fourier coefficients. So it's a space of functions where if you take R derivatives, then it will it will be an L2. And of course, you know, we know by Fourier duality that we can take the Fourier coefficients of this guy squared and multiply it by 1 plus k squared to the power of R. And we know it's quite, so okay, so it's quasi-compact, and what does that mean? If we take our unit disk, we will have some essential spectrum within some radius, which I'll call R of S. No, I'll call it rho of S. And then there will be some peripheral spectrum, which are our Wormell-Polycott resonances that live outside the spectrum. And we can always, as we can make S big, if we make S big, we make rho smaller. And so I suppose intuitively, what's going on there is that if you take a transfer operator, you take some very smooth function like this, and you apply your transfer operator, it's kind of, the form of the transfer operator is kind of like a weighted contraction, so it's going to expand a bit. So it's going to kind of like, you know, pull these things out, and so it's going to make it sort of smoother in a very kind of direct way. And so somehow you can imagine that the action of L is like a bit like a contraction, except for maybe some catch points. For most in most respects, it's sort of quite contracting. But if you take a kind of SCSI function like this, and you see what does it do to this, you're going to get something that's still kind of SCSI. So if your norm is like a measure, so if this norm is like a measure of regularity, then, well, if you allow these guys into your club to your Banach space club, then the kind of contraction for sort of most boring stuff that isn't geometrical about the geometrical information about your map, most boring stuff will decay here much. Well, if you don't allow these guys, then kind of you're going to get fast contraction to sort of the interesting features. But here you're going to get, if you allow SCSI things in with low differentiability, then the contraction is going to be slower. So this is kind of saying we haven't made our Banach space, you know, sort of small enough, full of, you know, the most dynamically relevant things. And okay, so, you know, usually when we have some functional analysis, okay, and I should also just say that the Koopman operator then is quasi-compact in the dual. So I suppose let's call it W minus R2. So you just weight the Sobolev space down. So I mean, these guys, if you have something in here, it's not necessarily an actual function, because this guy is strictly bigger than, let's say, L2. But it does contain things like delta functions or derivatives of delta functions. Or, you know, you imagine it's like you take L2 and you differentiate it R times. So somehow these are kind of formal objects, but of course, you know, all our nice functions live in there. It's just if they're, but they could be very oscillatory, but somehow that means their norm that doesn't affect their norm too much. So I think that explains that. So then we can ask ourselves, well, what does this this limiting Koopman operator actually tell us about, which I just rubbed out, as luck would have it. So The limiting Koopman operator is kind of saying, I'll just write it out again. So this is what I'm going to, so when I mean the limiting Koopman operator, I mean like you take the data limit. So this kind of continuum thing, it's psi naught naught infinity inverse times psi infinity naught naught. And these are kind of covariances between their entries are these guys. So they're kind of covariances between the functions with respect to mu, with respect to our sort of sampling measure times. So you can sort of rethink this as saying this is like a projection onto a sort of, let's say, at least an L2 mu projection onto our basis functions composed with the Koopman operator, which is going on there. And I suppose, you know, it's acting on, well, yeah, that's what it is. So we can ask ourselves, what is the, how can we actually, no, I don't want to get rid of this. I want to get rid of that. Yeah, so I guess we can think ourselves, well, okay, so if we're trying to understand how KB goes to K, this is like saying, how does this projection, I'm gonna ignore saying L mu. Maybe I'll put it up here if I want to, if it becomes relevant. So this projection question is more or less, how does this converge to the identity? At least when you put K in front of it. And so I will perhaps try and say something about that. And I'm going to do it on the left-hand side, sorry. Didn't really think about board presentation. I mean, in terms of, yeah, anyway. So we could start with a really simple measure, sorry. Yes, it's the orthogonal projection. So, you know, we've seen, like, I suppose one kind of orthogonal projection we've seen a lot of. So let's imagine that, let's say that we start with Lebesgue. So if we take, you know, a function, I'm going to call it A, and of course we can rewrite our function in terms of the Fourier coefficients. We can then ask ourselves, well, what happens if we project with respect to Lebesgue up to, well, okay, actually we need to say what our functions are going to be. So if we think about, let's just take our functions to be really simple things. Psi b is e to the ikx, or psi b is e to the ibx. There we go. So we're taking a Fourier basis, which is a very natural kind of simple basis. And of course, if we have a Fourier series, you know, we're going to say that our dictionary is going to be psi minus b up to psi b. Because, you know, this is kind of two-sided, it's not one-sided. So if we do that, we have pkleb, like the projection onto b basis functions of psi is just the sum from k as minus, or k, minus b plus 1 to b minus b plus 1 to b plus 1 of, so we're just taking the first b Fourier coefficients in each direction, minus b. And then, of course, we want to think about the difference between these guys. We get something like the sum with the absolute value of k is strictly bigger than b of ak e to the ikx. And so then, if we imagine, we go back to ideas of the Soto-York inequalities. If we go back to ideas of the Soto-York inequalities, you know, what we always need to do, well, not even the Soto-York inequality, just general discretization theory. What we need to do usually is to show that this guy is bounded from some weak space to some strong space. So if I think about, say, R S2 to R WT2 of, let's say, this function A, well, this is, if we square it, this is just the sum. This is just, I mean, the weighted sum of these guys. So sum from k bigger than b of ak hat squared times the weight that you get in a Sobolev norm, the power t. So we're going to do that. And well, this is somehow less than, but we're going to want to put in some other kind of weaker norm in here. So we can say that this is less than k bigger than b, ak squared times 1 plus k squared to the power of s. And now we have this extra term, 1 plus k squared to the power of t minus s. But because t, well, okay, let's imagine that we decide that, oh man, if we say that s is smaller than t, is that right? If s is smaller than t, then we have that this here is strictly less than 1 minus b. So if s is bigger than t, we have that this is strictly less than 1 minus b, and so then this is less than this guy here is the AWS norm times 1 plus b squared to the, so I should say minus s minus t. And so then if s is bigger than t, then this kind of is small here, and so we know that the norm of the projection is also small. Cool. Basically, Fourier projection is close to the identity if you imagine yourself starting with a very differentiable function and you take it to a very sort of non-different, like you take it to a sort of less differentiable function. It's like you get pointwise, you get good pointwise convergence of your Fourier system if you start with an analytic function. Maybe you don't get particularly good Fourier convergence if you start with a pointwise convergence if you just start with a continuous function. It's that kind of idea. And so how does this help us? Well, so I guess that's kind of the way that you should be thinking about these projections, but this is a very special projection because it's orthogonal projection with respect to Lebesgue. And so if we take our basis functions, somehow they really respect the norm. What's the time? Okay. 20 minutes. Okay, cool. Thanks. So, okay, so then I guess the question is what happens if we're not looking at Lebesgue? So again, this is a thorny question because there's, a million different kinds of measures you can have. But fortunately, if you're studying a, let's say a very smooth map, the best possible case in the world, then maybe we should say we can, well, yeah, if we're studying these kinds of ergodic measures of dynamical systems of circle maps, then we know that they kind of have, they have smooth SI physical measures. So we can assume that mu has some density where H is, I don't know, let's say analytic. Doesn't have to be, but let's keep it simple. So then we can ask ourselves, well, what does this projection do? Going from smooth to weak space. So, well, again, it's a bit hard because, well, okay, we could say, let's look at PK, which, well, okay, actually, one thing that we're going to do is we're just going to say, pretend, but here we're going to pretend that the basis, like it. I'll give you a theorem, and then I will tell you what we're going to pretend when we pretend to prove it. So the theorem is if that, let's say, the I minus PK from W S2, so do we start from W? Yeah, S2 WT2 with respect to this measure is less than this guy. So it's the same thing. It's as good as Fourier approximation. Well, I suppose then that we need to take to the minus S minus T 2. So it's as good as Fourier approximation up to some constant. And I guess this is me should be out in Sinum soon. So we have this result, and is there any bell and whistle here that we need? Oh yeah, so I guess we should say for all S bigger than T bigger than 0, this kind of least squares projection is basically as good as Fourier least squares projection. Yes. No, you don't change the weight. Sorry. So I suppose the idea is that, okay, so let's say the projection with respect to mu, the projection with respect to mu of some function is the, let's say the guy that minimizes, let's say you minimize over all possible, let's call it alpha k or b k, no, alpha k. So everything that lies in the span of your polynomials, of your observables, your trigonometric polynomials in this case, of psi minus phi with respect to the measure mu. With respect to this measure, yes, yeah, exactly. It's the orthogonal projection. So you can imagine, so if this is Lebesgue, then this is just the usual Fourier projection that's orthogonal in all your Sobolev spaces. There's, you know, the orthogonal projection if you change this. But if this is a different measure, then it's a different projection because you're changing the weight, and you can have, it's a different weight, it's a different projection, and so you sort of lose kind of the nice, you know, extension in sort of behavior with respect to the norms in these higher spaces. And in fact, you can actually get some really cooked stuff, some really kind of weird bad stuff if your measure is actually not, continuous. So you imagine that you have some, well, I mean, it's a bit like kind of interpolate, you know, you imagine that you have some, you know, some kind of Cantor measure with support. It doesn't have to be a Cantor, but a measure that's not supported everywhere. And you project, you have some function that looks like, I don't know, well, let's say you have some function that sort of is kind of wiggly like this. If your function is, and so it has a very small norm in most normal spaces. And if you get unlucky with this, so if this is phi, if you get unlucky with this is mu, then perhaps it could, you know, it could sort of tend to hit a bunch of kind of unrepresentative points here. And you might be able to project it onto your polynomials in a way that gives you something that looks like, where it just kind of goes crazy in the middle. So in this case, this looks a lot very unlike the Fourier projection of this phi, which is probably going to be, so this is p with respect to this measure. But if you look at the Fourier projection, it might be, you know, it's probably going to be quite, because that's with respect to Lebesgue, it's probably going to be quite stable and it's going to stay around here. So I think an interesting question is actually, does this kind of projection here play nice with dynamics that are, for which this measure mu is invariant? Just a side note. But certainly if your measure has a density, and I should say that h is always bigger than 0. If your measure has got a smooth density supported everywhere, then this kind of orthogonal projection behaves a lot like Fourier projection. And perhaps I could prove to you why this is, or maybe not prove to you, but give you a taste for why that is. I'm going to keep that. So the taste is as follows. Here we are. So let's imagine actually that we think about not, well, okay, let's imagine that we're only going to look at, changing our basis again, we're only going to look at psi, our basis is going to be e to the I, well, let's say 1, e to the ix, e to the 2ix, and so on and so forth up to e to the ibx. We could include the lower ones. It doesn't, I mean, it just adds some sort of little details that are not very cool. And imagine that we want to, that we can write, suppose we can write a function phi is a sum of ak e to the I kx, so positive. So somehow this phi extends into the upper half plane, is bounded in the upper half plane. So we can ask ourselves what happens if we do this projection on phi. Well, it's a bit hard to say it, write it in terms of these basis functions, but if we write it in terms of, we may be able to write it in terms of, let's call it ck, let's call it pk of x. If we write this in terms of these guys, which I'm going to call the orthogonal trigonometric polynomials with respect to mu, so which is to say that p j b k dx or d mu is delta jk. So basically, we're defining an orthogonal sort of set of functions based on this, and I suppose also we need to say that pk is a sum up to k of some constants. So I mean, if you imagine these as like polynomials of e to the ix, so I guess you could transform to the unit circle, then these guys are polynomials of order k, pk's or polynomials of order k, pj's or polynomial of order j. You can expand your function phi in this way, just kind of via a basis change. And so if you do this, then your function has a very simple expansion. K equals 0, and then this goes up to b, ck, pk of x. And so then, I guess if you want to understand I minus the projection, like the difference between the identity and the projection, like which is the error of the projection, of course, then you're interested in whether these guys are small. So it's really a question of like kind of, well, I suppose what is the Sobolev norm of these guys and how do these relate to those? And both of those questions can be answered by the following, well, okay, I don't want to say the following facts, but perhaps the following observation. As someone said in a talk, they were like, why can't you just say that, because, I guess we know everything about e to the ikx, but we want them to be orthogonal in with respect to this mu. So why don't you just say these orthogonal basis functions to be this? So, of course, the square root h of x, if you integrate pk with respect to pj, d mu, this is just the same thing as saying root h e to the ikx, e to the ijx, root h times h dx, which is what mu is. And then, of course, it all cancels out and you get the orthogonality, right? Of course, there's an obvious problem here, which is that this is not a trigonometric polynomial in general. But somehow morally, they are quite close to this. So if we write, in some sense, so for a start, we actually need to not use root h of x, but we need to, so I guess you can think of root h as e to the I, so e to the half log h. So I guess the problem with this is that it's not a sort of doesn't, I don't know, it doesn't quite give, as they say. What you actually want to do is you want to take the Hilbert, not the Hilbert transform, you kind of want to say take the Fourier transform of log h. You want to get rid of all the sort of negative Fourier coefficients of this. So let's say times 1, k is bigger than 0. No, we want to actually we want to get rid of all the positive Fourier coefficients of this. So we kind of do a sort of restriction of function h to only have positive Fourier coefficients. And we're going to call this instead some w. And the thing about w is that on the unit, like in the complex plane, it has quite a different analytic continuation to h, but on the real plane, it's so on the real line, its value, its absolute value is the same as root h. So it's somehow like, you know, root h times e to the I times some function. You can think of this as being h. And if you do this, then, well, again, these are not going to be trigonometric polynomials. What is actually true is that our orthogonal polynomials here look a lot like e to the I kx divided by this, sorry, that's not h, divided by this function w, which looks a lot like root h. And then, well, okay, somehow you, if this is the case, then we can perhaps try and define some, well, okay, one thing we know is that the Sobolev norm of the pk, I'll follow the plan, sorry. Okay, we can sort of define something like an operator u, which takes basically more or less what it does is it transforms orthogonal polynomials into e to the I kx's. So it's kind of a bit of an artificial operator, but more or less what it does is it sort of transforms these guys into something where the orthogonal projection is nice. So the projection with respect to mu is somehow u inverse of p of the Lebesgue projection times u. And because pk looks a lot like e to the I kx divided by this function w, u is basically multiplication by 1 on w plus something compact. And in particular, u and actually also u inverse are bounded in pretty much any norm you could possibly want in some sort of uniform bound. And this is enough to prove to you that this is the case, where this is, you know, somehow like I minus P leb okay, in the same norms. So I guess then I should, well, okay, should probably say how, yeah. It's approximately equal to that. Like as k gets big, it gets closer and closer to that. So somehow, you know, like for well, okay, so you know, for p0 is always just going to be 1. So p0 is always going to be, you know, a constant function. So that definitely doesn't look like 1 divided by w. But if you take, you know, if you say as k goes to infinity, you know, if w, this is kind of like the envelope of w, in fact, then pk is going to look, well, this is, I guess, the real part of pk, but it's going to look look at, say, the real part of pk, it's going to look a lot like my function, my e to the I kx times this envelope function, perhaps times a shift. Yeah, so I suppose how does the noise fit into this? Well, so what happens for this last limit? So in this last limit, it really does come down to those coefficients. So if we think about k, b, k, this is somehow, I guess it's actual k. plus the kind of this error here, which we know is something like e to the minus, well, something like b to the minus some polynomial, which depends on, let's say, let's look at this. So we need to think about this in terms of a norm, k of, let's say in WT. It's somehow like the error of I minus PK in WT with some weak space, let's say W naught, plus, I guess, the kind of error that you got between this error, which is the error of 1 on root n times a random matrix. I guess this is happening in Fourier space, so perhaps what we want to say is the Fourier transform of this guy in, let's say, WT. And this guy here we know is of order t to the minus, also b to the minus t. That's fine. This guy here, well, in L2, we know that this in L2 is of order, let's say, root b on root n. But then we're not looking at it in L2, we're looking at it in, okay, actually, this is minus. We have to take the adjoint because we're looking at the Koopman operator, but just put minus in front of everything. This is b on root n, but then we have to weight it by, the fact that we're weighting by this kind of 1 plus t squared to the power of, or 1 plus k squared to the power of t on 2. And so this actually gives us this extra constant out of b to the t. And if you do some magic, you can actually make that a lot. You can sort of do something else with this and get some exponential convergence because your map is exponential. Some psi bigger than 0. But the problem is, so then, somehow you get this kind of convergence. But if you want to look at your internal spectrum, you need better and better. Maybe okay, I would like to share my screen now. So what you get is that if you want to approximate something that is inside the outside the external spectrum of BT, so it's outside the external spectrum in one of these differentiable spaces, you just have to deal with this kind of BT penalty for your data error. So if your data is large enough, then it will work. But if you want to study anything inside here, then you have, as you keep going in and into your spectrum, you get worse and worse, you get higher and higher penalties on your data error, because this is these guys are really sort of higher differentiable objects of higher differentiability, essentially, these spectral objects. And so actually you can always kind of predict, you use kind of this sort of result, like these bounds on the essential spectral radius, you can actually predict which eigenvalues you'll be able to compute for a given ratio of data to, or log of data to log of observation size. You can see that you get essential spectrum inside it and good computations outside of it. But in practice, some of these guys are going to be almost impossible to compute unless you do something that's a bit cleverer than just standard EDMD on data. So there was a bit of a skip to that punchline, but yeah, this is there's some functional analytic connections here between there's connections between functional analysis of transfer operators and how what pieces of spectrum you can sort of practically approximate using data, which I think is kind of neat. So perhaps I should finish there, and thanks.
Are there any questions, comments?
So when you said one could do some magic to get exponential convergence, I suppose you change your Sobolev space to something more analytic?
No, it's actually, it's a lot cooler than that. So I think sometimes, I guess we tend to think in terms of, we have this idea of studying Alexey-Korepanov inequalities to do projection, to sort of, do numerics, and we say we project, and then we use Alexey-Korepanov inequality to get back. But we can also, one other thing that you can do is you can sort of study, I mean, if we have if our projection, the image of our projection is, let's say, E, and then there's some F, so that E plus F form our space. So that you can imagine that this maybe like the kernel of our projection often. Then if we separate our transfer operator into, let's say for an expanding map, if we look at our transfer operator specifically, not the Koopman operator, then that's just the transpose. We have, this is the thing that has all the that has all our eigenfunction or peripheral spectrum. This guy tends to contain, like this, the spectrum of this guy is usually just the essential spectrum. And this guy is often very small. And as it doesn't, and in a kind of space independent way, let's say the norm of this guy is the best possible, is somehow the smallest possible, the minimum overall of your space is that in which transfer, I guess W S bounded, so transfer operator bounded in WS of P K L. Morally it is about that. You can't prove it like this, but perhaps you could, I mean, what this actually is it is I minus PK transfer operator PK. And so in my 2019 paper on Chebyshev methods, which is generally, I mean, this was somehow the first kind of theorem proof paper I ever did, and I did it by myself, and so I didn't really know how to do it. So I was just stumbling around. I was working in I was doing a lot of weird things, but I didn't really understand Alexey-Korepanov inequality, so I actually kind of stumbled upon this idea, and so I could prove that that the transfer operators eigenfunctions converge. So usually traditionally you have convergence, let's say, of your eigenfunctions. Your eigenfunctions converge in the weak space, right? Projected, your computed converge to the true ones in the weak space, right? That's the kind of traditional convergence. But what using this idea is, what I could do there is I could actually show that it occurred in the strong space. And furthermore, even if you did study it in the weak space, the convergence was at the sort of blah, blah, blah. So and even if you did study in a weak space, or in the strong space, or whatever space you wanted to do, this convergence happened at the kind of, somehow the rate associated to this going from the strong space to L2. So so you use this kind of magic here to say, well, okay, if I have an analytic space, suppose I look at my convergence of things. I do it even though I'm looking in, some space of differentiable functions, if I can sort of show that this is small in that space of order e to the minus k analytic thing. And so one way you can do that for these kind of spectral methods is you just sum up the coefficients here. You just do a Frobenius norm bound on that, and it's provided that Frobenius norm converges, then it's going to be small. But I think there's other kinds of ways to prove it. So I mean, I'm curious if that works for something like Ulam as well, but I don't know. I don't really understand it, but
yeah, maybe we can discuss later.
Yeah.
And maybe a second question. So the picture that you have here,
yeah.
Do you take a system for which you have an essential spectrum?
No, I know I have. So okay, so the black dots, which are kind of getting lost behind the blue dots. The black dots are all discrete. This is an analytic expanding circle map. I can show you the map. It's this guy. So that's the graph of it. And it has the black dots of the spectrum, as a true spectrum. No essential spectrum, but here you see that you get something that looks numerically like essential spectrum, because you know, this is the sort of, I mean, I guess, you know, there's some Sobolev space where the data error is small. It's like small enough to be able to see anything. Whereas, you know, if you crank up your differentiability because you have this b to the t penalty on the size of the data error, if you crank t up, eventually that goes to infinity. And so like your approximation isn't actually anything close to where your true map is.
So it's just powers, I suppose, no?
Yeah, it's just powers, yeah.
And do you use a time series or do you use equidistant points?
Yeah, I use a time series. If you do, I mean, actually, to like get the true value, I like to get these black dots, which, you know, are good approximations of the true resonances. I use equispace. Yeah.
Okay. Yes. Thank you.
Oh, please welcome Alexey Korepanov, and he's going to speak from Loughborough University. And he's going to speak about high performance computing on a teapot.
Thank you very much. I'm very happy to be here, and the conference has been very interesting so far. I don't have any joke for this talk for a change, but the whole talk will be absolutely silly. It's silly not because I don't have any theorem to talk about, more because that I'll be talking about very basic and simple things to a sophisticated audience. And moreover, I'm not really an expert in what I'm talking about. But there is still something to say. And the premise is visualizations. So somebody has to talk about visualizations, right? So suppose you have done your computation. It could be complicated, but maybe it doesn't use anything extra special. And you want to share it with somebody. And this time you actually care about your users. So you want it to be easily accessible, reproducible. You want people to be able to play with it. You want it to be secure for them to run, in the sense that if I run your computation, I should be reasonably sure that it doesn't encrypt my files and ask for ransom or whatever. And you also want it to be stable, so you can come back to it 10 years after, 20 years after, and still get basically the same results. And the message of the talk is that in the reality we find ourselves in, this is often possible using most basic and widely available tools. And it begins for me with one of the most basic calculators you have available and installed on most of your devices. This is the browser console. Okay, it's in Italian. Which one is developer tools here? Okay, this one. Okay. Thank you very much. Okay, and this also can be sent to where's the console? Console. Okay, right, console. So every browser has quite a sophisticated ODE. There is a console, but there is also a debugger, network analyzer, profiler, and it understands at least a couple of languages. The most basic one is JavaScript. You just, it has a simple C-style syntax. You can compute basic things. You can multiply numbers. You can add strings. And the result is what you expect. It understands basic mathematical formulas, mathematical functions like trigonometry. This is available inside math, say math sine of math.py is, okay, it's pretty unusual, but this is 0, I hope you agree. It had been an actual 0 when I tried before doing this. So it's a C-style language, so you can write things like basic for loops. I apologize. I didn't expect the keyboard. Where is less? It will get better, I promise. I prepared, but okay. So some very basic facilities. This is it's a basic thing, widely available, but at the same time, it's one of the most sophisticated pieces of software. This language runs on a runtime which uses a just-in-time compiler. And often, if you write a simple program, it will run faster than a naive program in C, which is compiled by state-of-the-art compilers. It's a feature of the just-in-time compiler. When you run your code at first, it doesn't even compile it. It just runs it as a scripting language line by line. But when you write some procedure many, many times, then your runtime collects statistics and optimizes code specifically for the type of parameters which are fed in this. For example, if your parameters are small integers, it will optimize it for small integers and will get about as fast as machine code allows. So it is advanced, but we don't really care. As any more or less serious language, it has its quirks. For example, if you, so guess what this will be. I'll erase this question mark. B plus A plus A plus A. Does anybody have any idea what this will be? You think it will be BAAA? Yeah. So this is actually a banana. And another very interesting thing is if you square brackets. I need help from audience. How do I get a square bracket? Alt square bracket. Thanks. Alt shift square bracket. Alt square bracket. Square bracket. That alt. Okay. This is also alt. Thank you. So what is, can anybody guess what this will be? 4, 5, 6. Whoa! Sorry. So does anybody have any idea? Like if what? At both? Like Apple? No. So it won't be an apple. It'll be this. It converts them to strings and adds them. This is a dynamically typed language, and you have to, when you write code, really think about what happens to your types. It's a common problem. So this language has its problems, and it's not very nice for scientific computing. But for what we're going to look at today, we don't really care. So let's look at examples of how you use it in real life. So of course, you need some user interface, so you create some simple HTML. There used to be a time when writing HTML was hard. It's simple, then it became hard because you had to work a lot to make your page look nice. But it's back to being simple again for things which you need for presentation of your results. So you compile something very simple, HTML with body and P is a paragraph. Paragraph has hello, and it looks on the web page like this. Then you start using JavaScript. I told you it's very basic. So in the following example, it's almost the same, but you assign your paragraph an ID, demo, and you use a JavaScript to change the content of your paragraph. This is what happens when the document gets loaded, and it's exactly what you see. Right? So it's already very nice. You need no tools, no infrastructure. You can invoke code which changes whatever you see, and you can share it arbitrarily very, very easily. Next thing is you make it interactive by adding a button. It's also very, very natural. You add button with on click is what happens when you click on it. It's some function, and this function is described in the script tag. It looks like this. You click a button, and the button does what you say it should do. It gets increasingly complicated, but it stays easy. So in the next example, this is actually the easiest and fastest way for us to run LaTeX. It's ironic. The only thing to run LaTeX is your browser and simple HTML with JavaScript. These lines you just copy from MathJack's website. What they do is they pull a script from MathJack CDN, Content Delivery Network, and execute the scripts. The scripts will change what looks like LaTeX to mathematic formulas. This is all you need, and it looks all like this, right? Second thing is we want to be able to get pictures. You can write text, you can write LaTeX. This is already wonderful, but you also want to be able to draw images. In this example, we create a canvas. Canvas is just a square piece on which you can draw. Canvas with a border, we specify width and height, and we draw a line on it and a circle given by coordinates. And yes, this is what you do. And JavaScript is Turing complete. You can draw arbitrary lines. This means that the task of visualizations is complete as far as mathematicians are concerned. But well, you can do more. You can draw things, and you have a programming language which has loops. So you can draw circles in a loop. this loop clears my canvas and draws a circle, and the coordinates where the circle are, they change from frame to frame, and this becomes a billiard. So I find it very, very funny. This is the easiest way to simulate a billiard. It will run on every computer with a browser. It looks nice. It's very, very intuitive. Okay, let me give you a billiard then. So this is the next example is I couldn't refuse, and I asked ChatGPT to generate for me a code which animates a Sinai billiard with JavaScript. I won't walk you through this code, but it's more advanced than what I write. It's still very basic, but it has style. You see, it specifies how the document should look like, and it does look very nice. The code which is responsible for the billiard motion is just this function. It does something. I did not look at it. Does this look like a billiard? It's actually the right Sinai billiard. We often call a dispersing billiard Sinai billiard. Well, this is AI, right? So it generates something which kind of looks nice, and it doesn't care about what this looks like. No, I actually think that this is the original Sinai billiard. Yeah. When you write papers about Sinai billiard and actually mean a dispersing billiard on a torus, this is historically inaccurate. But it also depends on who you ask. Somehow ChatGPT got it right. It was very surprising. But languages are alive. So maybe if we call dispersing billiard on a torus Sinai billiard many times, then that will become correct. No, it doesn't care. Yeah, it also speeds up with time. So it wrote a code which is those lines. They are very similar to the true code which does it correctly, but there is some permutation, and maybe one of the minuses is in the wrong place. So it should be easy to fix. But yes, it's not quite correct motion-wise. Yeah, probably. But I didn't change it for the purpose of authenticity. So, all right, nice animations done easily. It's already great. The thing which is missing is plots. You want to build graphs, histograms, or whatever. My simple example here, it looks just like this. You create a data set, x coordinates, y coordinates. None is not a number, is a standard way to break a line. So I want to plot the doubling map. I want it to consist of two separate lines, and I insert none in the middle so that the points are not connected. This is not done by JavaScript or HTML themselves. I pull a library, which is one of the many libraries available for these kind of things. This is called plot.ly, the JavaScript version of Plotly. And I get a nice graph, which looks like a doubling map. Something slightly more advanced. I combine a graph with a LaTeX, and here we are. This is the Liverani-Sosova-Yenti map. Something which I have been trying not to think about for past couple of weeks with no success. We'll come back to it soon. Now, things are getting nice, but this is still not quite scientific programming. Next thing I want to show you is using parallelization. So it turns out that in JavaScript, it's very easy to spawn a worker. This code creates a worker with code from that file I'll tell you what this file does. It's something simple. This is enough to get that worker running, and then we communicate with it. We send it some payload. This is some arbitrary object. This time I ask it to do some number of iterations of whatever it does. And I create a handler for messages which come from the worker. In this case, I take what the worker gives me, and I modify LaTeX in my document to reflect it. So I'm going to ask a worker to do something very, very complicated. In this case, this is computing pi. You know that computing first 7 digits of pi can be very, very resource intensive. I consider a unit square with a circle, and I sample random points in the square. And I count the points which landed inside the circle and outside the circle. And then I compute a ratio and use it as an approximation for pi. This gives me very slow convergence, and it needs a lot of computational power. So this is what it looks like. We are waiting for the message from the worker. It has to do 200 million iterations. And while we are waiting for this, I have simple code which does the progress bar, these lines. So you can see that this actually happens in parallel. You always want to offload intensive calculations to the background, because otherwise this locks your UI and your web page hangs. So whenever you have to compute something really heavy, you put it in the background, and you can have many workers. It doesn't stop there. You can use a GPU if you have one. There is an API for GPU. So parallelization is quite strong. That's soon the end, but we still didn't cover anything related to scientific programming. I told you that I showed you examples where it looks counterintuitive, like when you add to arrays. So what if you actually have some code and you want to put it on a web page? In the next example, this is a short C++ code. I cannot have it all screen. C++ is not important here. C++ is my language of choice, but you can do the same with other mainstream languages like Go or Rust, and there is initial support for Julia even. Julia works partially, though it's a work in progress. So I take code which is written in C++. This time we take Arnold's cat map. This is a 2x2 matrix, and we raise it to an arbitrary power, which doesn't have to be an integer. We do it by importing eigen. Eigen is a very well established and robust library for linear algebra in C++. So this code is about as simple as it gets in C++. I create matrix, I do whatever the manual tells me to raise it to a power, and then I send it back to JavaScript. So everything except for these couple of lines is either loading libraries or the interface for mscripton, and mscripton is what I use to compile it into what can be used by JavaScript. This uses Clang toolchain, LLVM toolchain. LLVM is one of the standard compilers along with GCC. And the way it works is it takes your code and compiles it to bytecode. This works universally on every architecture. And then this bytecode is translated to machine code. So this time, we take this, we compile it to bytecode as usual, but then this bytecode is translated into what's called WebAssembly. It can be translated to JavaScript itself, and it used to work like this a few years ago. But now browsers support WebAssembly universally. It's a low-level assembly language, but it's higher level than the usual assembly language, so it runs on every architecture. So C++, bytecode, WebAssembly, and the interface is pretty straightforward. Then I use this code from the JavaScript side, this program has more lines than I'd like it to have, but what we actually have to look at, this is because of the interface. The line which sources the script, this takes the result of the compilation and gets it running. And this line, which calls my function I defined in my C++ code, it gets the result. So only 2 lines interface with the C++ code. And this time I should get an arbitrary power of the cat map. And my power here is just some random number. So let's see how it works. So there you go. Here's C++ running in a browser. It runs with near native performance, which is very good. You sacrifice only about maybe 10% or so. So it's really insignificant for modern computational resources. And of course, parallelization works. Very serious things have been ported from C++ or C to the browser, including computer games, which run on OpenGL, and they're translated to WebGL to run over here. Let me give you some example, maybe. Oops, sorry. quickjs.com. Anyway, Quake is a shooter game. Sorry, Pauline. Go ahead. Everything runs in the browser. Hmm. No, Paulina, exactly. Yeah, this is the later case. This is all run in your browser locally. If you want to interface with a server, then it's additional work. Yes, yes. You get the code, it's run in the browser locally. I mean, it's not universally so, but from what I'm talking about, this is so. If you create a server which runs something like when you play a game in a browser, a Quake, which I was trying to launch, that Quake has client side and server side. And then you have some. So things I talk about are entirely in the client side. This demo, my demo is on GitHub webpage, and this is an entirely static website. GitHub, the only thing it does, it serves you these files as they are, and the rest is handled by your client. Oh, actually, yeah, GitHub is very nice. GitHub belongs to Microsoft now, and I have a problem recommending them. It's a commercial company. You can do basically the same with the open source version GitLab. And the nice part about their infrastructure is that here in my repository, I have this EM CPP and EM HTML, but I don't store the compiled versions. But whenever I modify the C++ file, whenever I create a new commit, GitHub will spawn a temporary Ubuntu machine. It will compile my files to WebAssembly, and it will upload this to the web page, and it will run this. This is handled completely automatically, so it's very, very user-friendly. And you don't put garbage in your Git repository. You just keep the source files themselves. It's very, very nice. It's very user-friendly. So now, how much time do I have? Okay, I used quite a lot more time than I expected, but that's fine. Now I want to use my mad computer skills to ask you an actual question. The question is silly, but the implications are, at least they're very interesting. So just a bit of a background, I'll have to use a board. This is about the LSV map. LSV graph. LSV map as here. This is a map with polynomial decay of correlations. It depends on the parameter gamma. And there are 3 special points, values of gamma, when something very, very different happens. So gamma is positive. If gamma is 1 or more, then then the map preserves a sigma finite invariant measure. There is no absolutely continuous probability, invariant probability measure. So bigger than 1 is infinite measure. When you're smaller than 1, then the map preserves a finite measure. And at 1/2, you get a transition between central limit theorem and Levy alpha stable laws. There is another point here, gamma equals to 2. That is when things break on a technical level in renewal theory. I don't quite know how to explain it simply, but there is another point which is symmetric to 1/2, where things just go wrong. I want to look at the simplest way of memory loss for these systems. It's even simpler than decay of correlations. So I take a probability measure, mu, and I take it push forward under the map, push forward to power n, and you expect that this converges to, at least in the finite measure regime, it converges to the invariant measure. You can also ask this as you take 2 different probability measures, mu and nu, and the difference between push forwards, nu may be invariant or not. Difference between push forwards, you expect it will converge to 0. And the most basic way to measure distance between probability measures is the total variation. This is the same as L1 distance on transfer operators acting on densities of these probability measures, if densities exist. And it's a theorem that if gamma is less than 1 and probability mu and nu have sufficiently nice densities, such as smooth or belonging to the cone to which the invariant measure belongs, then this is at most n2 minus 1 over gamma minus 1. This result is sharp. But now, if both mu and nu have smooth densities, or even C1 would be enough, then you get a faster decay of correlations. You can remove minus 1 here. So if mu and nu have smooth density, this is a result by Sebastian from about 20 years ago, I think. I know at least 3 different proofs of this. I was trying to satisfy my own curiosity. So you have this rate n2 minus 1 over gamma, and it works for gamma smaller than 1, but this still decreases to 0. The right-hand side decreases to 0 when gamma is bigger than 1. So the question is, can you extend it to the infinite measure regime? And especially, can you make this transition continuous at 1? So can you keep the constant changing continuously when you cross 1? 1 is a very special point, is when your infinite measure changes to finite or the other way around. There are results about this. Actually, I think I know only one, and it's not quite the same. So this is part of the paper by Ian Melbourne and Dalia Terhesio. So when gamma is bigger than 1, and so on, you have T star and mu. These still have smooth densities. But now you look at this probability measure restricted to some interval epsilon 1 with epsilon positive, so away from 0. You still look at it in total variation. And this is still bounded by constant n2 minus 1 over gamma. So we know this away from 0. It's reassuring. Another, but there is a problem. One is that you don't really look at 0, where the blow up of the density happens. And the other is that these constants, they explode as you approach 1. So my question of extending these results to all gamma stands. And I was working on this with Ilya Cheverev. Ilya is a probabilist who does regularity structures in his normal life. We tried a lot of complicated things, and then we stumbled upon an argument which is very, very simple, which makes proofs of this, at least for this particular case of LC maps, a joke. I mean, it totally avoids most of the complications. So it's something very, very simple, but very interesting. But the proof is conditional on one thing which I wanted to ask you about. Also demonstrating my computer skills. So this is the map. And I look at the transfer operator, which works on functions which are C1 close to 1. The result I want is that these are the iterates of transfer operators. V is a function. In this case, it's 1 plus 0.05 times sine of whatever. I want these iterates of transfer operator to decay monotonically on the interval 1/2 1, where the second branch lives. So I want these lines to decrease to 0 monotonically. It could be monotonic up after some iterates, but these iterates should not depend on gamma. It should be uniform. Monotonicity is a rather special property. You probably can relate to this. If you have a series which is monotone and you, I don't know, estimate absolute values of increments, for example, then you don't need to take absolute values. Things just cancel. If you know anything about this, please talk to me. I might have a silly proof if I look at a version of the map which is like that. So I shifted to make the second branch very, very expanding and keep this branch nice. So in this case, I might be able to prove it, but my first 5 proofs were wrong. So what is the chance that this is correct? I don't know. Again, if you know anything about it, I would very much appreciate it. But the presentation is about computations. So here's an example of what you can do. I have a simple question I want to ask. I even added a slider. See, this is new and very fashionable. I can change the parameter of the map with a slider. Wow. And everything changed. And this iterate changed. And I can modify my function here. I can just change the formula and press set. Okay, I hope you at least enjoyed this. Sorry if it was too basic. Thank you very much. It's okay.
So are there any questions or comments?
Title. It was completely misguided. I wanted to talk about computation on everything. Like to make this able to run, you just need a JavaScript runtime. JavaScript runtime can be elementary. It can run on 8-bit processors. Or if you want to, if your teapot has a microprocessor, you see, then you can use it to run a web server and host these things. Or you can make calculations directly on it.
Are there any more questions or comments?
For what? So I use LaTeX. For LaTeX, I use mathjax. Let me see mathjax. But basically, I Google mathjax, and somewhere here should be the lines. Okay, somewhere here are the lines which I need to include into my HTML file, so it works. For graphs, I used Plotly.js. This is one of the many choices. There are lots of libraries which give you all kinds of graphs with different capabilities. I used this one because I could have a very, very basic example. But it's also very advanced. You can have 3D graphs, for example, and animations, and all kinds of things. For linear algebra in C++, I used eigen. But this is whatever language you are using, you probably know what kind of libraries you might want to use. C++ is in a way dominant. There are lots of things written for it. There are computer algebra systems which do symbolic computations. That's not very, very strong, but there is a lot. Yeah. It still works. Building might, yeah, okay, that's a good point. Eigen is particularly simple because it's header only, but you can use, I think I used MPFR, and it was about as simple as Eigen. I needed arbitrary precision computation, and you can find JavaScript libraries which do it, but they're quite annoying. So you can just use standard things available in the open source world for C++.
Caroline?
How safe it is to run it. So if I send you this file, how dangerous is it for you to open it? But it runs on your browser. It runs on GitHub. GitHub serves you static files. GitHub sends you text. That's all the interaction. You cannot break into whatever I do. You can read all my code because it's on GitHub, right? And you can see the history of commits. But the question is if I can break to you. So if I had a few spare $1 million, and went on a dark web and bought some zero-day exploit for the browser you use, and I knew which browser you're using, then maybe I would be able to do it. But it's a safe bet that probably I don't have a spare $2 million. So yeah, it's pretty secure. The sandboxes which browsers create to open whatever websites you visit are among the most secure things there are.
Oliver?
I'm curious about the stuff that
It's a JavaScript JSON plus runtime. So if you compile C++, then it will compile to. No, I was using mscripton. Mscripton is an extension of the LLVM toolchain, and LLVM is one of the standard compilers for C-like languages, Fortran, and some other things. So that's a serious bit of software which runs separately, which you cannot run in the browser. So compilation from C++ to JavaScript is handled by something sophisticated, which in this case GitHub does for me, and which is simple to run if you have a Linux machine to do it yourself. Yeah, exactly, yes. It runs in a workflow on GitHub. And then it compiles into WebAssembly. And WebAssembly is not JavaScript. It looks like this.
Oh, are there any more questions or comments? Sebastian?
Mhm. So JavaScript is very strictly standardized now. And browsers, it used to be a nightmare in the days of Internet Explorer, but Internet Explorer is gone. And now browsers are either Chrome-based or Firefox-based. They're just two popular runtimes, and they're pretty well synchronized. And the question for the community which maintains this browser is not just to make your page reproducible, but to make lots of websites which have been written still accessible, still running. So it just receives a lot of attention, and it's probably one of the most well-funded development things there is. Yeah. Good point. Yeah, but it's not just JavaScript problem. It's a generic problem.
I think that now WebAssembly is trying to complain to be IE 364 complaint. So they wanted to respect the floating point standard.
Did they not?
Discussion on this, but I don't know really. I think that you see where you have this E64. I think they are trying to yeah.
I think I've ran into similar issues with even C++ code. So yeah, compatibility of floating point arithmetics is an issue.
Is there any other question or comments? I'm curious. So your conjecture. So what you really need to prove is that some iterate of a C1 density is decreasing
All
0.5.
All iterates.
All iterates. Oh, okay.
At least from some.
Okay, so eventually it's decreasing.
For some iterate, but this number of iterates should be uniform for all parameters in the neighborhood of 1.
Okay. Are there any other questions or comments? So maybe we thank Alexey again.
Thank you very much.
Okay.